today I am going to discuss about the maximum subarray problem in algorithms. So first of all, the maximum subarray problem was proposed by Grenander in 1977 as a simplified model for maximum likelihood estimation of patterns in digitized images. Then we can looking to find a rectangular subarray with maximum sum in a two-dimensional array of real numbers. A brute force algorithm for the two-dimensional problem runs in O into n power 6 time. Because this was prohibitively slow, this is a big O of n power 6 times. Then Grenander proposed a one-dimensional problem to gain insight into its structure. Then it is derived an algorithm that's also one-dimensional problem in big O of n square time, improving the brute force running time of big O of n cube. Soon after, Shamos described the one-dimensional problem and its history at a Mellon University seminar attended by J. Caden, who designed within a minute and big O of n time algorithm, which is as fast as possible. Then about the maximum subarray problem, which can be done either by using the divide and conquer method or using the Cadence method. So let me discuss about the divide and conquer method. So the divide and conquer method, given an array an array that name is A of n real numbers, the maximum subarray problem asks to find a non-empty contiguous subarray of A whose values have the largest sum. The problem can be solved in big O of n time with a simple incremental dynamic programming algorithm that scans A from left to right. Since there is an obvious lower bound, this algorithm is optimal. The well-known divide and conquer approach to solve the maximum subarray problem involves splitting the array in half by the median index and making recursive calls on each of the two subarrays to find the maximum subarray on the left half and the maximum subarray on the right half. The combined step searches for the maximum subarray that begins in the left half of the array and ends in the right half. And overall maximum is then reported as a maximum of 3 left, right, and cross. Then this combined step requires a scan from the middle index of A to the left and to the right. So it's a T of n equal to 2T of n by 2 plus Cn. Then the linear time divide and conquer solution. So we start by noticing that in order to reduce the running time of the divide and conquer algorithm introduced earlier, we should be able to perform the combine phase in sublinear time. So to do so, we written additional information about the sum of the numbers in the recursive calls that can help compute the maximum subarray crossing the middle index in constant time. Specifically, if U is the current node and V and W are the left and right children of V, we compute the maximum contiguous subarray at U that starts in V, ends in W in O of 1 time. Then this is a diagram which represents our divide and conquer method. So if the problem that can be divided into the two subproblems, then the two subproblems can be solved. Then we can combine those subdivisions to a single solution. That's a divide and conquer method. We are dividing the whole problem into segments or the partitions, so which can be easy to perform our task. Then we can combine at last, which gives a optimal solution. Then as we discussed already, these two parts of the subarray are located in the left and right subarrays respectively. This is also evident from the two for loops in algorithm 2 and visualized. Second, the portion of the maximum crossing subarray in the left subarray of A is a maximum subarray ending at the middle index, and the portion in the right subarray of A is a maximum subarray beginning at the middle index. The maximum subarray problem find out the series of contiguous elements with the maximum sum in any given array. If all the elements in an array are positive, then it is easy to find the sum of all the elements of the array and it has the largest sum over any other subarrays you can make out from that array. But the problem gets trickier or more trickier when some of the elements are negative than the subarray whose sum of the elements is largest over the sum of the elements of any other subarrays of that element can place anywhere in the array. So this is the base case. So when I equal to r, there is only one element in the array and we can directly return the max subarray sum as x of 1 or x of r. Then it's a pseudocode for the divide and conquer. So it's a pseudocode. Then the main idea behind the solution is subarray which crosses a midpoint compromises a two subarrays x of I to mid and x of mid plus 1 to j. So we need to find the maximum subarray from x of I to mid and x of mid plus 1 to j and then combine them. So there's a time complexity which equal to the big O of 1 if n equal to 1. Then there is also space complexity. At each stage the input size decreases by 2. So the height of the tree will be big O of log n. Then we are at the end of the topic, this conclusion. This was possible because Cadence algorithm uses a technique to gather the information which is required to reach the solution, avoiding unnecessary storage of data, and hence this algorithm can be considered as a simple example of a dynamic programming approach with lots of practical application in the real world. Thank you.